Hello, this is the second video presentation from Machine Design Lesson 2. A lot of this material is going to be a review for you. Okay, so let's talk about direct stresses and deformation. These are normal stresses, and when I say normal stresses, they're normal to the cross section that's going to be carrying the material. So you got a long, slender rod, and then these forces are applied to the end of the rod. You're talking about either compression or tension. Tension, you tend to pull on the element. Those are positive stresses. And compressive, you tend to crush the element. Those are negative stresses. Shear stresses can also be direct shear, vertical shear, that's what you would have in beams, and then torsional shear. Okay, so when you have a part that's subject to a twisting load, it will have shear stresses in it as it twists. Let's talk about stresses and deformation in general. In this picture right here, we showed different types of loading. So here's your direct normal stresses, tension and compression. This little cartoon here shows what torsion is. And then here we're depicting shear stresses. And here is a flexure or bending stress. Direct shear stresses, when applied forces tend to cut through the member, that's what happens here. And then torsional shear stresses. Distribution of the stress is not uniform across the cross section. We're going to talk about that one a little bit more. You may or may have not had torsional stresses yet because it was originally talked about in advanced strengths of materials or advanced statics and strength of materials, essentially. Here's my cartoon with the formulas on normal stresses. Okay, this is an equation we all know very well. Sigma equals force divided by area. These would be direct tensile or compressive stresses, and there is your equation 3.1 for calculating the stress. Here are the units. I'll let you read through those. But this is an interesting part of it. You know, for this formula to be really valid, the load carrying member must be straight. And then the line of action of the load must pass through the centroid of the cross-section member. If not, you're kind of fooling yourself with this equation. That's kind of what I'm saying. It's easy to assume that, yeah, this is the equation and here's what we do, but it's also important to understand the conditions under which that equation is valid. Number 3, the member must be uniform cross-section near where the stress is being computed. And then the material must be homogeneous and isotropic, which means, you know, you can't have lumps of other stuff material in there. I mean, the material has to be the same. It has to be the same composition throughout. And then isotropic means that it has the same properties in all directions. So it has to be a certain type of material. And then if you're talking about a compressive member, the member must be short to prevent buckling. Again, that was something that came up in advanced strength of materials. So if you had a really long member under compression, then it could buckle. And then this equation is not necessarily valid for that. Okay, so for direct tensile or compressive stresses, this is our equation. Stress equals force divided by area. Now, if we're talking about deformation under those stresses, I'm going to offer this equation here. It's equation 3.2, where the deformation equals the force times the length divided by E, which is the modulus of elasticity, divided by A, which is the cross-section. And also notice that, you know, we can rearrange this equation a little bit because we know that stress equals force divided by area. So if we substitute that relationship in here, what we have is our deformation is related to stress times a length divided by the modulus of elasticity. Okay, so that's how we calculate deformation under axial loading. And there's a few examples in your example folder, in the problem folder that illustrate this. But again, these are not new concepts to you. The next one is direct stresses due to shear loads. The easiest way for me to depict a shear situation is the case when you had two members that are bolted together like this, and then you're applying a load on both of these members, and it tends to create a shear plane in the fastener that bolts these together, like right along this line here where the two parts meet. Okay, so this is single shear. Okay, so shear equals shearing force, in this case F, divided by A, which is the area that's in shear. In this case, this is one shear plane, which is the area of this fastener. Now, in this lower case, what we have is we have the same, essentially the same load, that's F, but we're carrying the shear load over two shear planes, and this is a condition we call double shear. Okay, so I want you to be aware of this when you're doing your homework. There's a couple problems where we talk about shear in pins. Okay, so when you're doing your homework, I need you to assume for me or write down your assumptions, whether you're assuming that the pins are sheared in a double shear or if it's a single shear type of arrangement. Okay. So next one I'm going to talk about, again, really quick, is shear stresses due to torsional loads. Okay, so stresses and deformation. Torsional deformation, when a shaft is subject to a torque, that's a twisting motion. It undergoes twisting in which one cross-section is rotated relative to the other sections in the shaft. Let me illustrate what that means. Okay, so here we got a solid shaft. We got our torsional. These could be like moments. You got either one end's fixed and you're applying a twisting moment at the other end, but if you were looking at the free body diagram of the shaft, you would have this twisting moment at one end, and then you would have an equal and opposite twisting motion at the other end. Here are the equations, and they show the distribution of stress due to torsion. As you can see, at the center of the axis of the part, stress is actually zero. Okay, so the generic equation for this is shear stress tau equals torque T times R. That is the radius. That is this radius right here, divided by J. Now J is the polar moment of inertia, and for a circular section, that's pi over 32 times d to the fourth. You can find these J, the equations for J, in the back of your textbook in the appendices. There is the appendix on the properties of areas, which is actually in Appendix 1, which starts on page 782. Okay, so that's how you find J, the polar moment of inertia. For a solid circular section, J equals pi over 32 times d to the fourth. These problems are really best off when you work in millimeters, but we're going to talk about that when we do examples. So here is your max equation. Your maximum torsional shear is always going to be at the outer fibers, because shear is at its maximum at the outer fibers of the part. Okay. Deformation. Torsional deformation. When a shaft is subjected to a torque, it undergoes a twisting in which one cross-section is rotated relative to the other cross-sections of the shaft. This angle of twist is computed from theta, which is our angle of twist, in radians, mind you, TL over JG, where T is the torque, L is the overall length, G is the modulus of elasticity in shear. Okay, it's given the character G, and it's also known as the shear modulus, or the modulus of elasticity in shear, and it's given this value G. Okay, now you got to be careful. This equation gives you twist in radians. If you wanted to convert this to degrees, you would have to convert it using the formulas. The next few slides talk about bending stresses in beams. And again, we're going to hit these a little bit harder next time, because I really don't give you any problems now in beam bending, because really what we do is we cover those a lot later, once again in when we talk about shafts. Okay, we talk about stresses due to bending and shafts, and so I'm just going to leave this one out of this section. I'm not giving you any homework problems in beam bending, because again, this material is a review for you. You covered it in statics and strength of materials, and maybe a little bit more in advanced strength of materials, but definitely you've seen it in statics and strengths. Okay, so we're going to limit it here to torsional shear, torsional deformation, shear stresses due to direct shear, and then stress and deformations due to normal stresses. That's your tension and compression. And that's all for these movies in the presentation of lesson 2. Thank you.